Good morning, students. Today we start a new chapter. Is a chapter of oscillators. In fact, oscillators are a group of self-sustaining circuits. When you switch on the circuit, it automatically gives out a sinusoidal output of a certain frequency. You have seen amplifiers where you give a sinusoidal input or any kind of waveform input and it amplifies the output. But oscillators, you don't need to give any input. Just switch on the circuit. That means DC supply to the circuit is switched on. The oscillator starts giving the output. Now, we shall see how it really works. For that, we come to this basic concept of a feedback circuit. You remember this is the basic concept of a feedback circuit. And this circuit, which I am showing to you, actually it's a negative feedback circuit because the signal which is fed back is subtracted. It is at the negative input of the summing amplifier. And the signal is at the positive input. So it is a negative feedback circuit. Where, if you have forgotten already feedback concept, I repeat, this is an amplifier which has a gain A, and this is a proportional circuit which has a factor of beta. That means whatever is the input comes to this feedback circuit, only beta part of it goes back to the feedback. Now, beta, of course, maximum value is 1. It can be less than, or it can be 1/10, it can be 1/5. Any part of the output is fed back to the input. This is the feedback circuit. And in the feedback chapter, we have seen if the open loop gain of this amplifier is A, that means without feedback, its gain is A. And if feedback factor is beta, then closed loop gain, that is closed loop output VO divided by VS, closed loop gain is A upon 1 plus A beta. This we have already seen. So no question about this. This is the feedback circuit gain, and we have learned various forms of feedback, etc. Now, look at this equation. First, theoretically, don't ask how it is possible. Theoretically, consider A beta is -1. A beta is -1. If that is so, then closed loop gain VO by VS becomes A upon 1 minus 1 equal to infinity. What does it mean? This is a circuit whose gain is infinite. What does it really practically mean? It practically means that there can be an output even when the input is 0. Right? That means the circuit will not need an input, but it will give an output. That means the amplifier produces an output even without any input signal. That is the requirement of an oscillator. So, a negative feedback circuit can become an oscillator if we can design A beta is -1. Or else, if it is a positive feedback circuit, and that means if this feedback input is also additive, then A beta should be equal to 1. That's all. So, this is the theoretical approach of an oscillator. What we have to do, we have to create a feedback circuit where A beta is equal to 1 if it is a positive feedback. And if it is a negative feedback circuit, A beta has to be equal to -1. So how do we do it? Now, we go back to a point where the open loop gain A, this open loop gain A of any amplifier is always frequency sensitive and is a complex number. If you don't believe it, then I'll give you a proof. Open loop gain A of any is a is a complex number and it is dependent upon A. Right? Now, we shall go to this point. We shall now go to separate circuit. We shall go there. We shall go to multi-sim simulation. We shall go to multi-sim simulation and I shall share with you the multi-sim simulation structure. Now you will be able to see the multi-sim simulation circuit. This is the circuit of a common emitter amplifier. This we have already learned. And we have tested this amplifier also a few times in this course. Now, what I am going to show you that gain is frequency sensitive. Now, you remember this was the board plotter, which shows this is the gain and x-axis, horizontal axis, is the frequency axis. So, of course, gain is frequency sensitive. So, my part of it is established that gain is frequency sensitive. Of any amplifier, gain is frequency sensitive. That mainly happens because of these capacitors used in this. And even if you do not use a capacitor, remember, any element in this universe or in this world has a reactance. It can be very small, but it has. So gain will be always frequency sensitive. Then I said the gain is a complex number, right? How? See, here the frequency is 1 kilohertz. You see the frequency is 1 kilohertz, right? And the frequency sensitive curve I showed you here earlier. The lower cutoff frequency is 15 hertz, upper cutoff frequency is 82 megahertz. Just look at this point here, right? So 1 kilohertz is mid frequency, somewhere in the middle where the gain is flat. Now, if we run this simulation, you see this input one is connected to in the blue line is the input, right? And red line is the output of the oscilloscope. So this blue curve is the input. Blue curve is the input. And this red curve is the output. See, there is approximately 180-degree phase difference between input and output. Now, when an amplifier or any black box electronic circuit creates a phase difference between the input or output, the transfer characteristics has a phase difference, then of course the transfer characteristics is a complex number. That means the transfer characteristics is in the form of A plus JB. Then only this phase comes. Now, this phase difference, this complex imaginary part or omega dependent part is also frequency sensitive. I'll show you this. Now, lower cutoff frequency is 15 hertz. Let us run this amplifier at a very low frequency of, say, 10 hertz, below the lower cutoff frequency, at 10 hertz, right? Then we run it and adjust the frequency scale 10 hertz, and output also I adjust so that you can see. Now you see the phase difference between the input and output is not 180 degree anymore. Clear? Is not 180 degree anymore. In fact, here the red line of the oscilloscope, red line of the oscilloscope is the output, blue line is the input. So blue line is the input and red line is the output. That means output is ahead of the input, but not by 180 degree. It appears it is ahead of the input by around 90 degree or less than 90 degree. Fine. In a bit portion, it was 180 degree ahead. Now it is only 90 degree ahead. Okay. Now let us make another trial. The upper cutoff frequency is 82 megahertz. Let us run this amplifier at 100 megahertz above upper cutoff frequency. When we run it at 100 megahertz, I have to adjust this. Now you can see. Now you see the output, this red line is behind the input. And it is behind about more than 90 degree, about 130 degree it is behind. That means at the flat zone of the frequency response, the output is 180 degree ahead of input. At below cutoff, it is ahead of input, but not 180 degree, much less, about 90 degree. And above upper cutoff frequency, the output is phase by phase, output is behind the input by certain degree. If you agree to this, then what we shall do, then we shall go back to our original PowerPoint presentation. Now you can see the PowerPoint presentation. Here, with the PowerPoint presentation, now we go back to this, our original point where we were, that what I was trying to prove to you, the open loop gain is always frequency sensitive and is a complex number. That means this A is always a frequency sensitive and a complex number. This A. Now I have to make A beta is equal to -1. That means -1 is a real number. If A is a complex number, then beta also has to be a complex number. To make the product A beta is equal to -1, there is no doubt in that. That means the feedback circuit also has to be a reactive circuit so that its transfer characteristics is a complex number, so that beta is a complex number. And then it is possible that at a certain value of omega or 2 pi f, A beta is equal to -1. Because beta also will be, this is open loop gain A plus j omega b. Say beta is equal to C plus j omega t. Then If beta you make a reactive circuit, then it is at a then at a certain value of omega, this imaginary part will cancel and A beta will be equal to -1. Now, if the circuit, that means A beta is equal to -1 is the condition for oscillation. And beta has to be a reactive circuit. Now, if the circuit you design as a positive feedback circuit, that means here you give it a positive additive input, then A beta has to be equal to 1. As simple as that. A beta is equal to 1 means mod A beta, that means the magnitude of A beta has to be 1 and the imaginary part of and the total phase shift has to be equal to 2 pi or multiple of 2 pi. That means mod A beta, then angle of A beta has to be 2 pi or multiple of 2 pi. Now, this condition was first studied by a scientist called Berkhausen. He has named it as Berkhausen criteria for oscillation, that A beta, mod A beta, magnitude of A beta has to be 1 and total phase shift from here back to here has to be equal to 2 pi. This is called Berkhausen criteria of oscillation. Okay. Next, we shall study a few types of oscillators. Now, basically, there are a few classes of oscillators. The class of oscillator that we study first is RC oscillators, where the feedback circuit is comprised of resistors and capacitors. And among RC oscillators, the common one is the phase shift oscillator, right? As usual, there will be amplifier. Now, this amplifier I have shown you is 741, the op-amp based. This could be a JFET amplifier, could be a BJT amplifier, anything depending upon how you design it. In that case, this is the amplifier, and this is the input resistance R1, output resistance RF. You have possibly already learned in op-amp based amplifier design, and gain of this amplifier is RF by R1. And this is the feedback circuit. This is the feedback circuit. And now, op-amp, I have given the input to the negative input. That means there is already 180-degree phase shift. And from here, the output, part of the output goes back to the input. From in between this feedback circuit, I create another at 180-degree phase shift. And each RC combination produces 60-degree phase shift, total 180-degree phase shift. So signal suffers a phase shift of 180-degree here, another 180-degree here. So total 360-degree or 2 pi angle phase shift, 2 pi, and that means the Berkhausen criteria is satisfied. And the values of R and C and RF and R1 has to be so designed that A beta becomes equal to 1. Angle part is already satisfied by these reactances. Now, so the feedback is in phase with the input. That means when there is a 180-degree phase shift, the feedback is in phase with the input. And in phase input means it is positive input, right? Now, there are two Zeners we need in phase shift oscillator. That is to limit the output to the amplitude of Vz. This has nothing to do in the feedback circuit. Now, the frequency of oscillation and the values of RC, etc. in phase shift oscillator is a lengthy process of deduction. And I feel personally that you need not, you can study it at home, but you need not remember that. It's not essential. It's a very long deduction. What do you remember? What is the output frequency Oscillation frequency is 1 upon 2 pi under root 6 RC, which comes to 0.065 by RC. You remember this relation, 0.065 by RC. And also, RF by R1 has to be more than 29. These are the two relations you remember so far as the phase shift oscillator is concerned. Okay. Now we go to another type of RC oscillator, which is called Wien-Bridge oscillator. Here again there is a amplifier. I have shown you op-amp based amplifier. It could be any amplifier. But this amplifier is in a negative, non-inverting mode. That means input is given here. The feedback input is given to the positive input of the amplifier. Right? It's in a non-inverting mode. In phase shift, it was an inverting. That was only difference. And there is a series RC combination and a parallel RC combination. Here, this R1, RF, and this RC in series and this RC in parallel, they form a bridge. You see, these are the two diagonal points of the bridge in which there is a amplifier and it is connected to the output, and another end of the bridge is the common, because this common and this common is same. So the four arms are R1, RF, RC parallel, and RC series. They form a bridge, and that's why it's called Wien-Bridge oscillator. And this oscillation of this oscillator works when the bridge is balanced. Bridge is balanced and it is at resonance. Just remember once again, because the deduction is very lengthy, its frequency of oscillation is 1 upon 2 pi RC. That means 0.159 by RC. Another condition is this RF has to be equal to 2R1, because the gain of this amplifier need to be 3. And gain of the non-inverting amplifier is 1 plus RF by R1, which is equal to 3. That means RF by R1 is equal to 2. That means RF equal to 2R1. So you remember this relation and this relation. Just remember these two relations and the structure of the Wien-Bridge oscillator. Now, before going to LC oscillator, let us see how Wien-Bridge oscillators works, right? So we go to simulation point, simulation circuits. We go to phase shift oscillator. This is a phase shift oscillator. This is the amplifier. You remember, this was the RN, R1, this is the RF, and input goes to the inverting input, and this is the RC, 3 RC combinations, and these are the amplitude limiting Zeners, right? So this we have done already. Now, and this is the output is connected to the oscillator, right? Now, gain here is RF by R1. You remember, for phase shift oscillator, gain has to be more than 29. Here, RF is taken 1 megohm and R1 is 33 kilo, so gain is around 30.3. And also remember the equation, frequency of oscillation is 0.065 by RC. That means 0.065 by R. Here, every R is 3.3 K. So 3.3 K, and every C is 100 nanofarad. 100 nanofarad, if you calculate this, it is 197 hertz. So frequency should be 197 hertz. So this is a phase shift oscillator. Now let us run the phase shift oscillator and see what happens. Nothing happens. Why? really nothing happens. I switched on, but nothing happens. That is because if you go to another practical aspect, we have seen that an oscillator, it has a gain infinity. So it has an output when there is no input. But think of the very initial instant, very initial first microsecond after switch on. If there is no input, how can there be any output? Sinusoidal output. In practice, when you do all these things in your laboratories or in your industries, what happens? There is a environmental electrical noise, whose technical name we call it thermal noise, because 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 of the temperature or environmental temperature in your circuit, every element of your circuit, actually electrons are flowing through them randomly, and it creates a thermal noise due to vibration. That we call noise, thermal noise. The noise chapter is not there in your BTech course. I remember it is in your postgraduate course. It's a very interesting and very complex subject. It's a complex chapter. Anyway, what do you remember? There is a noise. Today's in digital era, there is always a electromagnetic wave noise around us for mobile signal, Wi-Fi signal, this, that, everything. Now, this noise practically contains all frequencies from almost zero to almost infinity. So when you are assembling and testing a circuit in your laboratory, this noise is there at the input of your circuit. And that noise may be a nanovolt noise. That noise is amplified. And that is given a feedback, positive feedback, which is again amplified. And again, there is a positive feedback, which is again amplified. So within a fraction of microsecond, your output, your oscillator starts generating the output without but you do not know that it has started due to the environmental noise. And once it has started, and since the factor A beta is equal to 1 is true only for one frequency, because both A and beta is omega frequency dependent. So A beta is equal to 1 relation will be satisfied only at one single frequency. So that particular single frequency will be the output. Now, when I am simulating this in my computer, there is no noise. So oscillation does not start. So if you are simulating this in your computer, then add a thermal noise element here. And for starting of the oscillation, just close this switch and then you open it, it will start oscillating. So I shall show you once again. I start, there is no output. I close this switch, open this switch, output starts. Well, once the output starts, you don't need any noise. And this is the frequency which is equal to around 197 or 100 or around 200 hertz. So this is how phase shift oscillator works. Okay. Now we shall also see Wien bridge oscillator. This is the Wien bridge oscillator. You remember the feedback is given to the non-inverting input, and there is a series RC combination, there is a parallel RC combination. This is RF by R1. Very simple configuration. And RF by R1 has to be 2. Here it is 24K by 12K, so ratio is 2. And the frequency relation was 0.159 by RC. That means 0.159 divided by R is 3.3K, C is 50 nanofarad. It is around 964 hertz, around 1 kilowatts. Right? Once again, I start simulation. Nothing happens. I close and then open this switch. Oscillation starts. Right? This oscillation is around 1 kilowatts oscillation. So this is how your wind bridge and phase shift oscillators work. Okay. In our next lesson, we shall see another type of oscillators. These are the RC oscillators. In our next lesson, we shall see LC oscillators. Right? So we close this lesson today here. Next, we shall go for LC oscillators.